Okay, sorry for the confusion about that. I'm Tyler Jones, and I'm a PhD candidate at the University of Colorado. The talk today is Interpretation of High-Frequency Oscillations in West Antarctica. We're looking at the Waste Divide ice core water isotope record. And it was the first water isotope record measured from surface to bedrock using continuous flow analysis. And we have over 8 million simultaneous measurements of hydrogen and oxygen ratios. So at Waste Divide, the oldest ice is dated to about 60,000 years before present, and we have an annually resolved chronology to 30,000 years. The water isotopes themselves are mainly a proxy for local temperature and regional atmospheric circulation. So to give you an idea of the record that we're working with, I want to compare low versus high resolution sampling. This is a plot of delta D versus a depth of 2,060 meters. You're looking first here at half-meter low-resolution samples from the University of Washington from the same ice core. And when we overlay the University of Colorado record, you can see the amount of information we're working with. The depth here at 2060 is about 12,000 years before present, and we're still seeing remnants of a yearly cycle in the water isotopes. So the overview of the talk is just quickly what influences the water isotope record, why we have to do a diffusion correction to fully understand the record, and then the main point is high frequency oscillations. We'll look at 2 to 15-year oscillations and how those have changed over time back to 30,000 years. So Waste Divide right here is located in inland West Antarctica. It's upslope from the South Pacific sector of the Southern Ocean, and so it has influences coming from the Pacific, which I'll talk a little bit about in a second. But when you look at a water isotope record, the dominant signal is a one-year signal. It represents local near-surface atmospheric temperature dependent on the seasonal cycle and random weather events. What we're interested today in is the short-term oscillations between 2 and 15 years, which are more dependent on regional oceanic atmospheric circulation patterns like the southern annular mode, and the El Nino southern oscillation, and other undefined internal noise. So there's a lot of research that has gone into the climatology in West Antarctica, and I'll share some of it with you here. Teleconnected ENSO climate signals are pervasive across the continent. And ENSO, the El Nino Southern Oscillation, has been shown to affect atmospheric circulation, local temperature, and snow accumulation. And there's a positive correlation between ENSO and the southern annular mode during times of strong teleconnection. And one other piece of background info that I wanted to share with you is that when we're looking at these short-term oscillations between 2 and 15 years in the ice core, those oscillations are not stationary in time, and we wouldn't expect them to be. And a good way to illustrate that is a central tropical Pacific coral record from Urban in the early 2000s. And over the last 150 years, they found decadal variability, times of 3-year variability, a period of general sub-decadal variability, and then after 1976, 4 years. So it's non-stationary in nature. So a quick summary before I go forward. We effectively have the highest resolution record the ice core can offer, both in terms of high frequency and it spans the glacial-interglacial transition. The ice core location has a range of non-stationary climate influences, tropical, polar, and other internal noise. We're interested in looking at high frequency oscillations between 2 and 15 years, and we think the results will inform discussions about climate modeling and potentially abrupt climate change triggers or amplifiers. So, as I mentioned before, if you want to fully understand this record, you have to quantify diffusion. And you can do that by solving for a diffusion length, which is the average displacement of a water molecule from its original position along the vertical axis. This mainly happens in the firn column of the ice sheet in the upper 90 meters or so of ice. And the diffusion corresponds to a smoothing by a Gaussian filter, which I'll show you here. You're looking at a plot of power density, so we're in the frequency domain, versus frequency. and it's a 500-year window of data from about 3,000 years ago at Waste Divide. The spectrum is shown here, and we're fitting a pink line to it, a Gaussian, where the sigma variable we can use to pull out a diffusion length. And so what I have here is diffusion length shown in years on the y-axis. Sometimes you'll see it reported in terms of meters, but for this study I'm using years. And then time back to 30,000 years on the x-axis. And we're solving for diffusion length in 500-year windows. The things that affect diffusion are mainly temperature and accumulation, plus the thinning or strain of the ice, and a little bit from impurities. Okay, so we have our diffusion lengths, and what we can do with that is we can go back and do a back diffusion of the spectral power. So here again, power density versus period. The red line here is what you expect to see in an ice core. This is observations from about 14,000 years ago. Again, the high frequencies due to diffusion have less power, and we're using our diffusion lengths to estimate what the spectral power would have been at the surface of the ice sheet. And my next slide, and the next two are very important. They're mainly the conclusions of the talk. We're going to look first at the classic ENSO band, as I'm calling it, between 2 to 7 years, and look at that through time to see how it's changed. So here we have a plot of average power versus time, and the red is the observations from the ice core between 2 to 7 year oscillations, so that's the integrated power, and blue is the back diffusion. And so I'll just go over a few take-home points here. One is we see no trend in the Holocene power, and this is different from a number of GCM studies that suggest reduced ENSO variability over these oscillation bands around 6,000 years ago due to insulation forcing. So we don't see that in Antarctica, at least how this is expressed there. And then more importantly, the glacial power is 2 to 4 times as large as the Holocene power. It's more variable. There's places that appear to have abrupt transitions in nature, and there's some sort of millennial trend in here. So we've never seen a record like this before, and we're investigating what some of these things might mean. So I want to switch over to a 4 to 15 year oscillation band. And if you weren't sure about the back diffusion calculations or the spectral estimates, if we look just at the red line again, you'll notice that the power in the glacial is still 2 to 3 times as large just directly from the observations. And then because 4-year cycles and higher aren't really subjected to diffusion, the diffusion correction is not that much greater for these bands. And there's an interesting transition here for these bands that include the decadal periodicities around 16,000 years before present, about a factor of 2, a little bit less than that, decrease in the power there over a quick transition. So the general idea is we wanted to introduce this record due to the amount of information we have and start to think about these high-frequency oscillations. Again, the Holocene showed no trend. The glacial is anywhere from 2 to 4 times larger in power than the Holocene. There appear to be millennial trends, but we want to investigate that further, and there are some abrupt shifts. So the next steps for this study is we have a deuterium excess record that we're finalizing, and that's mainly a sea surface temperature proxy, so that can add to the knowledge we have here from the water isotopes. We want to take this information and compare to NCAR models, and finally start thinking about abrupt climate change mechanisms and whether this can inform anything in that debate. Thanks.
All right, we have time for a few questions. Anyone?
So you mentioned you're looking at the effect of ENSO, but what about other things like the AO, since you're going from that type of high variability when you have a lot of ice cover in the northern hemisphere to much less variability after diffusion?
Yeah,
Sorry, will you repeat the question?
so she asked about the fact that we're looking at ENSO and whether there's other things such as the Antarctic, or the Antarctic oscillation. Arctic. Oh, Arctic oscillation. The thing with this data set is we can't directly link any of the oscillations to any of the other oscillations occurring in the climate system, like ENSO, like the southern annular mode, like the AO. We know it plays into it, but backing that out is very hard. And so what we have is an expression of all those things that happen in the climate system as it occurs in Antarctica.
How strong do you think is your signal affected by changes in the source region or your size?
That would be useful to look at in the models. First off, we don't know for sure, but the deuterium excess is a great source variable, and so we can use deuterium excess to maybe find differences in the two records and sort that out.
Another one from there. Just
Also,
repeat.
El Nino just makes a small percentage of the variance of temperature, rainfall, variability in Antarctica. I'm wondering whether SAM and El Nino have different influences on the covariance between temperature or the delta 80 or deuterium excess, so that by looking at different proxies, you can actually differentiate between the different modes and their contributions.
Yeah, agreed. It's a good point. Not much to say. I agree with you.